Let's get started with lesson 3-6. The title is When is an inverse not a function? So a little blast from the past, inverse functions. I know we've already talked about them some this year. You learned about them in Algebra 2 last year. So when we get started with this first warm-up problem, this is a review, but we will go through it together. It says find the inverse of f of x if f of x is equal to 3 times the quantity of 2x plus 2 raised to the negative third power. Interesting. All right, so let's get started. So I'm going to recopy my function right here. I have 3 times that quantity of 2x plus 2, and then we're raising it to the negative third power. Well, remember, there are several ways you can do this. You can list out all the steps and then undo them and re-record them. You can do the switch and solve, right, where we have y equals 3 times a quantity of 2x plus 2 to the negative third power, and then we take it and switch our x and our y like we've been doing here in the previous sections. Let's do it that way here because this one's a little bit more complex. We have x equals 3 times the quantity of 2y plus 2 to the negative third power. So the first thing I'm going to recognize here is that negative 3 as the exponent. I don't like that. So let's rewrite this expression so that it has a positive exponent. We're just going to move our quantity of 2y plus 2 down to the bottom so that becomes a positive third power. So to solve this, right, so what we want to do is let's take it and let's cross multiply. So we're looking at doing, 3 times 1, for cross multiplying, doing 3 times the 1, and then we're doing this expression times x. When we do that, we end up with 2y plus 2 in the parentheses raised to the third power times our x is going to equal 3 times 1, which is just 3. Next step, let's get rid of the x. So let's just divide each side of the equation by x. And we're looking at 2y plus 2, all raised to the third power, is going to equal 3 divided by x. Now we need to get rid of that third power, so let's just take the cube root of each side. And that leaves us now with 2y plus 2 is going to equal the cube root of 3 divided by x. And we're just trying to solve this for y, so let's just keep going, right? This part's probably the easier part. We'll subtract 2 from each side. 2 times y is equal to the cube root of 3 divided by x minus 2. So that's outside of, the cube root. And last, let's just divide everything by 2. So I get y is equal to, and you can write this several different ways. Remember, if I take this and I split this apart and said the cube root of 3 over x, and if I said I was dividing this by 2 and then subtracting 2 over 2, right? I gave them each their own denominator. Okay, sometimes that's a little bit easier to do. And then I know that taking that expression right here and dividing it by 2 is the same thing as multiplying it. So it's like a 1/2 times the cube root of 3 over x. And then when I subtract 2 over 2, really that's the same thing as 1. So I'm going to subtract 1. And that is going to be our inverse. So the inverse of function f would equal 1/2 times the cube root of 3 over x minus 1. Now, are there some other variations or ways you could write it? I'm sure that there are, but we're going to go with this one for right now. If you have a question about yours, if you did it differently, just reach out to me and ask, and we can figure it out. Let's look at the next part. Find the inverse of function f if f of x is equal to 2x over the quantity of x plus 2. All right, let's just do a little switch and solve again. Right, we'll start with y is equal to 2x over the quantity of x plus 2. When you switch and solve and you have two x's, you are still going to replace each of them with a y. So I'm going to put x equals 2y over a y plus 2. Okay, so we're just switching all the x's and all the y's. So anything that was an x is now a y, and anything that was a y is now an x. Let's cross multiply here. We've got x times the quantity of y plus 2 equals 2y. And because we have a y inside our grouping symbols and a y over here, and we're trying to get y by itself, we have to find a way to combine those. So we need to break this y out of the grouping symbols that we've got here. And the way we're going to do that is just distribute the x through. We have x, y plus 2x equals 2y. Now let's get all our y's together on the same side. And we've got 2x is equal to 2y minus xy. Now we can take it and we can find a way to write just as a single y, right? They both have y as a factor. So if we factor out y, we're left with 2 minus x equals 2x. And then we're just going to divide each side by 2 minus x. And that will get us our answer of 2x over 2 minus x equals y. Or if you're writing it in function notation, the inverse of function f is going to equal 2x over 2 minus x. If you have questions about that, please make sure you reach out. Let's move on. Next slide talks about inverse relations. We already know that in order to find the equation of the inverse, we switch the x and the y coordinates. This is also true when graphing inverses. Two relations are inverses if and only if one relation contains the point BA, while the other contains the point AB. So in other words, the x's and the y's are flip-flopping places between the two. Here we have the inverse graphs, y equals x squared and x equals y squared. It says visually a relation and its inverse are symmetric, right? So this is supposed to say, and its inverse. Sorry, something happened there. So visually, a relation and its inverse are symmetric across the line what? So think back to Algebra 2, when you drew in this line, which separated them. That is the line y equals x. So they are always symmetrical across that line, y equals x. For each graph, state the domain and range. So for y equals x squared, which is this one, we know that our domain is all real numbers. And our range is going from 0 to positive infinity. We got a bracket on the left and a parenthesis on the right. Looking at the inverse, okay, we're looking at the inverse. It asks for our domain. Well, our domain, right, if we think about it, starts over at 0 and then goes to the right forever. So we're going to say our domain goes from 0 to positive infinity. Our range looks like it's going to be going up forever and down forever. So that's going to give us all real numbers. The important thing about doing this right now is remember, our x's and y's are switching. So you should see this happen on your paper here where the domain of the original function ends up being the range of its inverse. And the same thing is true about the original range has become the new domain. With inverses, we flip-flop our x's and y's. Therefore, the domain and ranges are going to flip-flop as well. That is important to know. The next slide says, shown below is the graph of function f. If f is a function, sketch the inverse of f is the inverse of function. Okay, so a couple ways we can look at this. First of all, we already know that this original one is a function. Y equals f of x is a function. And if you think back to things like, you learned probably in the past the vertical line test, right? If you drew a vertical line through a function, anywhere on the function, And if it only touches at one time, then it is going to be a function. So this one is a function because of that, right? I could take this vertical line that I have, right, and I can move it back and forth across here, and it only intersects that function one time ever. Okay, now, if I wanted to graph its inverse just by using the graph, what we're going to do is just create a little table over here and record some points. So we have x and we have y. And we'll just choose some points that we can see easily. So it'll be -2, 0. I want to choose this one because it's a maximum and where it's shifting directions. So we have -1, 4. Then we've got a point right here at the point 1, 0. And then we'll use that point 2, 4 next. All right, so remember, if our function is changing to its inverse, that means each of the x and the y's will end up switching places. All of our coordinates will flip-flop. We've got 0, -2, 4, -1, 0, 1, and then 4, 2. Let's plot those new points on our graph to see what it looks like. So 0, -2, 4, -1, 0, 1, and then 4, 2. And if we try to connect them now, we're going to run from down here underneath. We're going to come, we're going to go up through, we're going to hit it, bounce, come down, hit it, bounce, and go this way. I don't think I quite hit them there. Sorry about that, but I think it looks okay. All right, and if you're not sure if it's right, I mean, you can visualize this other graph, touching its, actually, let's just do this. This will be fun, right? I'm going to take this graph. If I move it over here, you can see how it has that reflection across that line y equals x, right? I'll put it back over here, but that's important to know. Okay, so is the inverse a function? Well, if I take it here and I draw a vertical line down through it, you notice I hit it in multiple places there. So is the inverse a function? No, the inverse is not, but the original is, yes. Now, something you can do sometimes, it's called the horizontal line test. If I take my original function and I draw a horizontal line and I hit it more than one place, I know its inverse is not going to be a function because that's why that line hits it in more than one place when I do it this way. So the horizontal line test will tell you if the inverse is a function or not, based on whether or not it intersects the graph more than one time. All right, so shown below is a graph y equals 2 to the power of x minus 3. Sketch its inverse on the same set of axes, then state the domain and the range for each. Okay, so if we want to do our inverse of this function, first thing, let's look at here is let's think about trying to do our table where we're going to take it and we're going to flip them around. Okay, so if we think about our original graph, right, it's got a horizontal asymptote that runs right down here where where y equals -3, right? So our asymptote right here is going to be where y is equal to -3, which means we're going to have an asymptote for our inverse where x equals -3. So if we put that on here, you're going to see this asymptote that runs right down here. Okay, now we just need to come up with some other points to plot on here so we can see what our inverse function is going to look like. So I'm going to make a little table for my originals, and then we'll just flip-flop them to make our inverse. So our original graph, and actually I'll write these in blue since the original graph is in blue. Let's just choose a few points. Let's see, we've got the point right here. It looks like it's the point 0, -2. We've got a point here, looks like at 1, -1. We've got a point at 2, 1. And we'll choose the point that's up here. Looks like the point 3, 5. For our inverse function, we know that those are going to switch places. So we're going to have one at -2, 0. We're going to have one at -1, 1. We'll have one at 1, 2, and 5, 3. And let's just plot those. So -2, 0, -1, 1, 1, 2, and 5, 3. And we can see it's going to run right along the asymptote, come up, hit, curl out, and then shoot out this direction. Looking at our domains and ranges, the domain of our original function is going to be all real numbers. It goes left and right forever. Our range, though, goes from -3, and we're going to exclude that value because it's an asymptote, to positive infinity. And now when we look at our inverse, remember, our domains and ranges should switch. So our domain should become our new range, and our range should become our new domain. And if we look at it here, that kind of makes sense because we're going from here over this way for our domain. So we're going to say -3 to positive infinity. And then our range is going down forever, and then it's going to end up going up forever. So that's going to be all real numbers. So our domains and ranges ended up flipping again. All right, so last one we have, given y, graph it and its inverse. Is the inverse a function? So we have an absolute value function. Looks like it's going to be flipped, vertically compressed, and it's been shifted up 3 units. So if you want, you can take it and you can graph it first if you're comfortable with graphing it. If you need to come up with a table first, you can do that. Okay, I think I'm pretty good with graphing it here, so I'm going to go up to +3. And then I know it's flipped, and my slope is -1/2. So I'm going to go down 1 over 2, down 1 over 2, down 1 over 2, and then the same thing going the other way. There is our function. Now, you can use that to help you create your inverse, right? If you just want to take it and list out some points, I have a point at -6, 0, point at -2, 2, 0, 3, 2, 2, and 6, 0. That's our original function. If we want to do its inverse now, okay, so we'll come up with our points here. We're just going to flip-flop them. So starting out flip-flopping -6, 0, you should have 0, -6. Then we have 2, -2. Then we have 3, 0. Then we've got 2, 2, and then 0, 6. Let's plot those on our graph and see what they look like. I'll do them in red. So 0, -6, 2, -2, 3, 0. Then we're going to 2, 2, and then 0, 6. And if we go ahead in here and try to connect those, you'll see we get our shape. And you can see here already that, right, it is a reflection across this line, y equals x, which with that and the other function, the original. Our domain for the original is going to end up being all real numbers. Our range goes from -infinity all the way up to 3, and that includes 3. And so I already know here that this range is going to become my new domain for the inverse. So I'm going to say -infinity all the way to 3. And then my original domain becomes my new range. So that's going to be all real numbers. All right, that's it for this section. If you have questions, please make sure you ask. This is a lot of stuff from the past, but we're just trying to combine it with what we're learning currently to make something new for you. All right, have a great day. Thanks for watching.